Welcome to Lesson 4, the final lesson of Focal Area 2. In Lesson 1 of Focal Area 2, we learned about the 6 components of a scientific project. In Lesson 2, we learned how to ask good research questions and formulate testable hypotheses. In Lesson 3, we learned how to identify variables and design fair experiments. In this lesson, we are going to learn how to conduct the experiment, collect data, analyze results, and draw conclusions. We are also going to learn how to communicate your findings. By the end of this lesson, you will be able to conduct a complete scientific project from start to finish. You will be able to collect accurate data, analyze it, draw valid conclusions, and share your findings with others. This is where all planning comes together. This is where you will discover the answer to your research question. So let's get started. Now, it is time to actually conduct your experiment. This is where all your plannings comes to life. But before you start, let me give you some important reminders. First, follow your procedure exactly. You spent time planning your procedure for a reason. Every step is important. If you skip steps or change the procedure, you might get unreliable results. Second, record data carefully. Write down your measurements immediately. Don't wait until later to write them down. Don't rely on your memory. Write down the exact values. Include units like centimeters, grams, seconds, whatever is appropriate. Third, keep control variables constant. Remember, you want to keep everything the same except for your independent variable. If you are testing different fertilizers, make sure all plants get the same amount of light, water, soil, and pot size. Fourth, replicate multiple times. Do your experiment 3 times. This gives you more reliable results. Fifth, note any problems or changes. If something unexpected happens, write it down. Maybe a plant got knocked over. Maybe the temperature was unusually high. Maybe you forgot to water one group. Write it down. This information is important for your analysis. Now, what if something goes wrong? Don't panic. In science, problems are learning opportunities. If something goes wrong, note what happened. Explain what went wrong. Decide if you need to repeat that trial. Learn from the mistake. Don't hide problems. Problems are part of science. Scientists encounter problems all the time. What matters is how you handle them. When you conduct your experiment carefully and thoughtfully, you produce reliable data. And reliable data leads to valid conclusions. Before you conduct your experiment, you need to plan how you collect and record your data. What should you record? Record all measurements. If you are measuring plant height, record the height. Record the height of every plant in every group. Record observations. Maybe you notice that some plants look healthier than others. Write that down. Record times and dates. When did you take each measurement? Write it down. Record any unusual occurrences. Did anything unexpected happen? Write it down. Record environmental conditions. What was the temperature? What was the humidity? Write it down. How should you organize your data? Use a data table. A data table has columns for different measurements and rows for different observations. For example, if you're investigating how different fertilizers affect plant growth, your data table might have columns for the date, the group, the plant number, the height, and the number of leaves. Each row would represent one measurement. A well-organized data table makes it easy to see patterns and compare results. Let me give you an example. If you are measuring plant height every 3 days for 6 weeks, you might have table with columns for the date, the height of plant in group 1, the height of plant in group 2, the height of plant in group 3. Each row would represent one measurement date. When you organize your data this way, you can easily see how how plant height changes over time in each group. You can easily compare the groups. You can easily spot any unusual values. Organized data is the foundation of good analysis. Now that you have collected your data, it is time to analyze it. Analysis means looking at your data carefully to understand what it shows. Here are 5 steps for analyzing your results. 1. Organize data. Create tables and graphs to make your data visual. A graph is often easier to understand than a table of numbers. If you are measuring plant height over time, a line graph will show how height changes over time. If you are comparing the final height of plants in different groups, a bar graph would show the comparison clearly. Second, look for patterns. Do values increase or decrease? Are there any unusual values? Do patterns repeat? For example, if you are measuring plant height every 3 days, you might notice that plants in group A grow faster than plants in group 2. That's a pattern. Third, calculate averages. If you did 3 trials, you have 3 measurements for each group. Add them up and divide by 3 to get the average. Averages help you see the overall trend and reduce the effect of unusual values. 4. Compare groups. Compare the experimental groups with the control group. Did the experimental groups perform differently from the control group? If so, how? 5. Identify trends. Does your data show a relationship? For example, does plant height increase as fertilizer amount increases? Does dissolving speed increase as temperature increases? When you analyze your data this way, you start to see what your data is telling you. You start to understand what happened in your experiment. When you analyze your data, you probably want to create graphs. Graphs make data visual and easier to understand. There are three common types of graphs. First, a line graph. A line graph shows changes over time. If you are measuring plant height every 3 days for 6 weeks, a line graph will show how height changes over time. You would have time on the axis, x-axis, and height on the y-axis. You would plot a point for each measurement and connect the points with a line. If you have multiple groups, you would have multiple lines, one for each group. A line graph makes it easy to see trends over time. Second, a bar graph. A bar graph compares different groups. If you are comparing the final height of plants in three different groups, a bar graph will show the comparison clearly. You would have the groups on the x-axis and the height on the y-axis. You draw a bar for each group. The height of the bar shows the height of the plant in that group. A bar graph makes it easy to compare groups. Third is a scatter plot. A scatter plot shows relationship between variables. If you are investigating how temperature affects dissolving speed, you would plot temperature on the x-axis and dissolving speed on the y-axis. Each point represents one trial. If the points form a pattern like a line going up or down, that shows a relationship between the variables. A scatter plot makes it easy to see if there is a relationship. When you choose a graph type, think about what you want to show. Do you want to show how something changes over time? Then use a line graph. Do you want to compare different groups? Use a bar graph. Do you want to show a relationship between two variables? Use a scatter plot. The right graph type makes your data easy to understand. Now comes the exciting part, drawing conclusions. A conclusion is where you interpret your results and decide what they mean. Your conclusion should include 5 elements. First, was your hypothesis supported? You look at your data. Did it support your hypothesis or not? Say yes or no clearly. Then explain why. For example, if your hypothesis was if plants receive more sunlight, then they will grow taller, and your data shows that plants receiving more light did grow taller, then your hypothesis was supported. Explain that the data shows plants receiving more sunlight grew on average of 5 centimeters taller than plants receiving less sunlight. Second, what does your data show? Describe what you found. Don't just say the hypothesis was supported. Describe the actual result. For example, plants receiving chemical fertilizer grew an average of 15 centimeters. Plants receiving organic fertilizer grew an average of 12 centimeters. Plants receiving no fertilizer grew an average of 8 centimeters. And third, explain why you think this happened. Link your results to scientific principles or prior knowledge. For example, chemical fertilizer provides nutrients in a form that plants can easily absorb, so plants grow faster. Organic fertilizer provides nutrients more slowly, so plants grow more slowly. Plants receiving no fertilizer have limited nutrients, so they grow the slowest. Fourth, identify limitations of your study. What could have been done better? Maybe your sample size was small. Maybe you only tested for 6 weeks when you could have tested for longer. Maybe you only tested one type of plant. Identifying limitations shows that you understand the strengths and weaknesses of your study. Fifth, suggest future research. What would you investigate next? For example, in the future, I would like to investigate how different amounts of fertilizer affect plant growth, or I would like to test this with different types of plants. When you include all five elements, you write a strong conclusion that shows you understand your results and their meaning. The final step is to communicate your findings. This is where you share your results with others. There are three main ways to communicate your findings. First, a written report. A written report includes several sections. The title tells what you investigated. The introduction explains why you investigated it and what you already knew. The method section describes exactly how you conducted your experiment. The results section presents your data, usually with tables and graphs. The discussion section interprets your results and explains what they mean. The conclusion section summarizes your findings and suggests future research. The references section lists the sources you use. A written report is thorough and detailed. Second, a poster presentation. A poster presentation is a visual display of your project. It includes your research question, hypothesis, methods, results, and conclusions. It uses graphs, diagrams, and images to make the information visual. A poster presentation is good for sharing your work at a science fair or conference. Third, an oral presentation. An oral presentation is where you talk about your project to an audience. You explain your research question, your hypothesis, methods, results, and conclusions. You use visual aids like slides or posters to support your explanation. An oral presentation is good for sharing your work in class or at a conference. Why is communicating findings so important? Because science is not just about doing experiments. Science is about sharing knowledge. When you communicate your findings, you allow others to learn from your work. You allow others to build on your work. You contribute to the collective knowledge of science. When you communicate your findings clearly and effectively, you help others understand your work. You help others see why your work is important. You help others use your findings to solve problems or answer questions. You take time to communicate your findings well. Make sure your writing is clear. Make sure your graphs are easy to understand. Make sure your presentation is engaging. When you communicate your findings effectively, you complete the scientific process. Let's summarize what we have learned in this lesson and throughout focal area 2. You conduct experiment carefully following your procedure exactly. Every step matters. Record data accurately and organize it in tables. Organize data makes analysis easier. Analyze data by creating graphs and looking for patterns. Graphs make data visual and easier to understand. Draw conclusions that explain what your data means. Your conclusions should address whether your hypothesis was supported, what your data shows, why you think it happened, what the limitations were, and what you would investigate next. Communicate your findings through reports, posters, or presentations. Sharing your work is an important part of science. Now, let me ask you some reflection questions. First, Why is it important to follow your procedure exactly? What would happen if you didn't? Second, how do graphs help you understand your data? Why are they better than just looking at numbers? And third, what would you investigate in your own scientific project? What are you curious about? Throughout this focal area, you have learned how to design scientific projects. You have learned how to ask good research questions and formulate testable hypotheses. You have learned how to identify variables and design fair experiments. You have learned how to conduct experiments, collect data, analyze results, and draw conclusions. You have learned how to communicate your findings. These are the skills that scientists use every day. These are the skills that will help you solve problems throughout your life. You are now ready to design and conduct your own scientific project. Choose a topic you are curious about. Follow the 10 steps we have discussed. Design a fair experiment. Collect accurate data. Analyze your results. Draw valid conclusions. Communicate your findings. You can do this. I'm excited to see you discover.